Hi. This is my video on the basics of finding limits. So we're going to start off with the definition of a limit, which is a limit is the height a function intends to reach at a given x value, whether or not it actually reaches it. So I'm going to try to explain what I'm doing and what things mean as I work out these problems. So we're going to start off with a simple function. So f of x is equal to 2x plus 5. And that's this graph right here. I already drew it out so that we could save some time. So we know that the line has a slope of 2 and a y-intercept of 5. That's the basic y-intercept form. If I were to plug in x equals 3 into this equation, I would get f of 3 is equal to 2 times 3 plus 5, which obviously equals 11. Okay, that's very simple. What does this mean, however? It means that the point 311 belongs to the relation and function I call f. So it means that the point 3 of 311 falls on the graph of f like this. 311. Now say that we don't know that f of 3 equals 11 for whatever reason. We can still find what it would possibly be by plugging in numbers close to 3. So basically guessing and checking. So say 2.99999. So f of this number equals 10.99998. Oh, I went off my little paper there, but that's okay. It's pretty obvious that f is headed for the point 311. And that's what's meant by a limit. It's heading toward that point. It's going this way. It's going up toward 311. So if you plug in any number that's really, really close to it, that's what it's going to be. It's going to go up to that. So in this example, we determine that the limit as x approaches 3 of f of x equals 11, because the function approaches a height of 11 as we plugged in x values closer and closer to 3. This is written like this. So the limit, you see that? The limit as x approaches 3. So you put a little x and then as it approaches 3 with an arrow pointing to 3. Of f of x equals 11. So this is the basic thing about limits. So it's read, the limit as x approaches 3 of f of x is equal to 11. That's the limit. That's the answer. Okay. So this graph represents the function g of x is equal to x squared minus x minus 6 all over x plus 2. Okay. Obviously the domain of G cannot contain x equals negative 2. Because that makes a 0 in the denominator. See, we have like a kind of like a fraction thing there. So it'll make the denominator 0 if you plug in negative 2 into x. So if we know that, if you substitute x equals negative 2 into g of x equals x squared minus x minus 6 all over x plus 2, you get 0 over 0, right? 0 over 0, which is said to be an indeterminate form. Typically, a result of 0 over 0 means that a hole appears in the graph at that value of g. So you see the hole down here? I kind of drew the graph off, but there's a little circle that's not filled in here. That's the hole. So that's what that means when you get 0, 0 as an answer when you plug something in. 0 over 0. That's what it means. It's got a little hole somewhere on that graph, on that point that you plugged in. So the hole, where was I? Hold on, okay. The hole at x equals negative 2 is where we are going to evaluate that limit, right? So there's a hole there. Okay. So we will evaluate the limit as x approaches negative 2, since that's where the hole is. So the limit as x approaches negative 2 of g of x, that's what we're trying to find, equals what? That's our thing there. We gotta figure that out. So this okay, this is just like we did in the last example. We could plug in a number close to x equals negative 2, and in this case I'm going to do x equals 1.99999. Okay. Yeah, that's enough nines, I think. So g okay, it has to be negative here because you're going towards x equals negative 2. That's the thing there. So it's got to be negative. So g of negative 1.99999 equals negative 4.99999. Okay, so I bet you can't guess what this is going to be, because negative 4.99999 is definitely close to 5, negative 5, on the function g when x equals negative 2. It's insanely close to negative 5. So we're going to say that the limit as x approaches negative 2 of g of x is equal to negative 5. So this is the guess and check way of doing this. Even though the point negative 2, negative 5 does not appear on the graph of g, it's still gonna this is still gonna be the answer. This is one example of a limit existing because a function intends to go to a height despite not actually reaching that height. In this example, we determined that the limit as x approaches 3, as x approaches negative 2, keep thinking this is a 3, of g of x is equal to negative 5. Okay, so now we're going to get into some rules. So if you did not understand anything else from this video, you have to at least try to understand this. I'm going to try to explain when a limit does exist and when it doesn't. In order for a limit to exist on a function f, at some x value, then three things must happen. The first rule is that the left-hand limit must exist at x equals c. The right-hand limit must exist at x equals c. That's the second rule. Third rule is that the right and left must be equal to c. I think I could have just put one rule that they have to be equal at c, but that's okay. By the way, the left and the right-hand limit is when you're looking at a graph. This would be the left-hand limit because it's coming up from the left. This would be the right-hand limit because it's coming from the right. So that, if you didn't know that, that's what that means. Oops. Okay. There are two interesting x values on this graph. X equals -1 and x equals 6. At one of those values, a general limit exists, and at the other, no general limit exists. Right? Okay. So, the limit as x approaches -1 of f of x exists, and the limit as x approaches 6 of f of x does not. As you approach x equals -1 from the left and the right sides, each time you are headed towards the height of 5. The height of 5, so it's going up to 5. So you can see 1, 2, 3, 4, 5, 5. It's going up to 5. So the two one-sided limits exist and are equal, and we can conclude that the limit as x approaches -1 of f of x equals 5, because it's going towards 5. This is 5. It's going up towards 5. This is another way I like to, if you have a graph, if you just have a graph in front of you, this is the absolutely easiest way to see if it exists or not. This graph does exist. This is my personal way to tell if it exists or not. So, this is point C. They both have to exist at point C. So they both have to have like -c, -1. I just drew this graph really quickly so I don't have accurate, points. And then this one would have to be -c, 1, 2, 3, about 3. That's easy. They both have to have c in there. So all you have to do, basically draw a line, a little bridge here, and see if they connect. And they do. So that's the easiest way to find out if this exists, and this does. This one exists. It's very, very simple. Now, if you have one that's like this one does not exist. Because these points these lines never ever have the same c value. They never have a c value. So usually these graphs that look like these are they're not equal. I mean, my bridge metaphor, or not metaphor, my bridge theory is not always accurate because you can always draw a bridge right here, but the bridge thing doesn't matter. When it looks like this and it never ever has a c value, like if they never have the same value here, like they never, you know what I mean? They never have this value. They never have the c value in them, no matter what. So this value doesn't exist. And that concludes my video tutorial. I hope it helped.